This is Mrs. Mooney's notes for Chapter 12, Sound. Sound waves are longitudinal mechanical waves that are produced by vibrating objects. When an object, such as your vocal cords, vibrates, it causes the air molecules to alternately bunch up or compress and then spread back out. When these trains of compressions reach your ear, tiny bones begin to vibrate and your brain interprets this as sound. You can see that the sound waves are longitudinal. Look at the direction the material, the air molecules are vibrating in the same direction as the propagation of the sound wave. Both are going horizontally here. Compared to a transverse wave, where the direction of the wave is horizontal, but the air molecules are vibrating vertically here. So this would be a transverse wave. Longitudinal waves, such as sound waves, are made up of compressions, areas where the medium, such as air molecules, are all bunched up, and then areas where the medium have spread back out again, called rarefactions. So, and a wavelength for a longitudinal wave is made up of one compression, one rarefaction, and the wavelength would be measured from rarefaction to rarefaction. As we learned in the last chapter, the amplitude of a transverse wave is measured by the height of the crest, or the trough. The amplitude of a compressional or longitudinal wave depends upon how dense the medium is at each compression. In other words, how tightly packed the material is at the compression area. This spring here, A, would be more dense than spring B, because spring A's compressions, the materials are more tightly packed, more close together. Here, the material is a little less dense, a little spread out, so the amplitude would be less. Also, remember, the amplitude is a measure of the energy. So the greater the energy is of the wave, the more tightly packed the material would be in the compression, and the greater the amplitude. Sound waves travel through solid, liquid, and gases, the velocity of which would depend upon the density of the material and the temperature of the air. The more dense the material, the faster sound will travel. And here you can see as the density of the material increases, so does the speed of the sound wave. Also, the higher the temperature, the faster the particles of the medium are moving. They have more kinetic energy and will carry the sound faster. The speed of sound in air is 331.5 meters per second at 0 degrees Celsius, and it will increase at 0.6 meters per second per degree. So we'll generally use the speed of sound of 343 meters per second at room temperature, which is typically taken at 20 degrees Celsius. And this value is obtained by 331.5 plus 0.6 times the 20 degrees above zero. Actually, I think you get 343.5, but unless told otherwise, use the speed of sound at 343 meters per second. Sound waves can be reflected. Those are your echoes. Sound waves can be diffracted, which means they bend around edges of objects or through small openings, such as doors, so you can hear people in another room. And sound waves can interfere with one another, both constructively and destructively. Pitch is a measure of how high or low a sound is, and it depends upon the frequency of the sound wave. Sound waves that have a very low frequency and therefore would have longer wavelengths would have a low pitch. So low frequency, long wavelengths, low pitch. And you can remember low frequency, low pitch, like a foghorn or a lighthouse horn. Then as the frequency increases, notice the wavelength decreases. But at any rate, high frequency sounds have high pitch, like a screaming girl or a police siren. The human can generally hear frequencies in the range of 20 to 20,000 hertz. Humans cannot hear below 20 hertz, Sounds below this level are termed infrasonic. Infra means below, sonic refers to sound. Sounds above 20,000 hertz are termed ultrasonic, above sound, although some animals, most notably dogs, can hear frequencies in this range in which you would not be able to hear.
Sound is a transfer of energy caused by any vibrating material and is transmitted by longitudinal waves. Sometimes they are called compression waves. This slinky toy shows how it works. Notice how, as it is pushed out, some rings of the slinky bunch up and others are spread out. If we could see the longitudinal waves of sound, this is what they would look like. When a sound wave is created, the wave of energy moves outward from the source, pushing the air molecules back and forth parallel to the direction of the wave motion. The molecules next to the source of the sound are forced outward and bump into other molecules, passing the sound vibrations on to them. And so the energy of the vibrations radiates outward. When the wave arrives at the audience, the molecules vibrate the individual's eardrums, and the listener interprets the vibrations as sound. The sound waves have carried the energy of the music through the medium of the air. A medium can be air, water, or any solid material. It is essential for the transmission of sound because there must be molecules to vibrate and transfer the energy. We can't see the sound waves in the air, but it can be easily demonstrated that sound creates waves. This tuning fork is vibrating at 440 cycles per second. When dipped into the water, a disturbance caused by the vibrations is clearly visible. The waves of energy have been transferred to the water. Our perception of sound is shaped by the nature of the wave. When a loud musical note is created, the amplitude or height of the wave is greater. The louder the noise, the higher the wave. The waves of this high-pitched note have a high frequency. This means that it is producing far more waves per second than this low-pitched note. The higher the pitch, the greater the frequency of waves. The human ear can hear a broad range of sounds, from 20 hertz to about 20,000 hertz. In other words, we can hear frequencies from 20 waves per second to about 20,000 waves per second. Other animals can hear a much wider range of sound. Dogs, for example, can hear sounds up to 40,000 hertz, and bats up to 100,000 hertz.
The Doppler effect is the apparent change in frequency detected by an observer when a source of sound is moving relative to the observer. When a source of sound, such as a train blowing its whistle, moves, the sound waves pile up in front of it and strike the observer's ear with an increasing frequency. The observer's brain then interprets this as a higher pitch. Higher frequency corresponds to higher pitched sounds. Once the source of sound moves away, the sound waves spread out and strike the observer's ear with a less frequency, and the decrease in frequency is interpreted as a lower pitched sound. If the source of the sound is moving towards an observer, the sound waves bunch up and begin to strike the observer's ear with more frequency, more waves per second. This is interpreted as an increase in frequency and pitch by the observer. As the sound source moves away from the observer, the sound waves spread out and strike the observer's ear with less frequency. This is interpreted as a drop in frequency and pitch. The Doppler effect is common to all waves, including electromagnetic, and occurs every time there is a relative motion between the source of a sound and an observer, i.e., the observer could be moving, or both the source and the observer could be moving.
In the phenomenon known as the Doppler effect, Sound waves that are approaching an observer have a higher frequency than sound waves that are moving away from the observer. This can be illustrated by the sound of an approaching train whistle. The pitch of the whistle appears to increase as the train approaches and drops in tone after it passes. This occurs because as a train approaches, sound waves of the whistle are crowded together, producing shorter wavelengths and therefore a higher pitch. As it passes, the wavelengths increase in length and the pitch of the whistle drops. This phenomenon also occurs with stars. Stars moving away from the Earth have a shift towards the red, or lower end of the spectrum, while stars moving towards the Earth have a shift toward the blue, or high-frequency end of the visible light spectrum.
Let's try a few practice problems. A train moving at 40 meters per second sounds its whistle, which has a frequency of 500 hertz. What frequency would be heard by a stationary observer as the train approaches? Would this frequency be higher or lower than 500 hertz? And would this be interpreted as a higher or lower pitch? Well, since the train is moving towards the observer, the sound waves would be piling up and striking the observer's ear with an increase in frequency. So the frequency would be interpreted as greater than 500 hertz, and the sound would be interpreted as a higher pitch. What frequency would be heard by the observer as the train moves away? A higher or lower than 500 hertz frequency, and would this be interpreted as a higher or lower pitch? Well, since the source is moving away, the wavelengths would be spreading out, reaching the observer's ear with a decrease in frequency. So this would be interpreted as lower than 500 hertz and would correspond to a lower pitch. The frequency of a school bell is 2500 hertz. If you are driving towards the school at 10 meters per second, what frequency would you hear? Higher or lower than 2500 hertz? And would you interpret this as a higher or lower pitch? Well, this works the same way as the source of sound moving towards the observer. If you are moving towards the source of sound, the sound waves would be piling up and striking your ear with an increase in frequency. So you would interpret the frequency as greater than 2500 hertz and interpret the sound as a higher pitched sound. Loudness or volume of a sound depends upon the amplitude of the sound wave. The greater the amplitude, the more energy the sound wave has, and the louder it is. Sound intensity, symbolized by I, is defined as the power output of the sound divided by the area the sound wave is covering. Recall, power equals energy divided by time. The units for power is the watts. And sound radiates outward from the source in all directions, so the area is that of a sphere, which is determined by the formula 4 pi r squared. Thus, intensity would equal power measured in watts divided by the area, which would be determined by 4 times pi times the radius of the sphere squared. The units for intensity is watts per square meter. And although loudness is not measured directly by intensity, in general, more intense sounds are louder. What is the intensity of a 75 watt stereo at a distance of 1.5 meters? The power, measured in watts, would be 75. The stereo at a distance of 1.5 meters, well, 1.5 meters would be the radius of the sphere produced by the sound wave at that distance. So the area then would be 4 pi times 1.5 squared, or 28.26 square meters. And if intensity is power divided by area, the intensity then would be the 75 watt power divided by the 28.26 square meter area, which gives you a final answer of 2.7 watts per square meter. Loudness is closely related to intensity. The intensity of a sound wave approximately determines its perceived loudness. However, loudness is not directly proportional to intensity. For humans, loudness is approximately a logarithmic scale. See the formula here. However, we won't be working with the formula. Just realize that it is a logarithmic scale and that for every increase in 10 decibels, the sound intensity increases by a factor of 10. So, for an example, if you wanted to look at the change in sound intensity going from a whisper at 30 decibels to normal conversation at 50 decibels, the intensity would not increase by a factor of 20, but by a factor of 10 times 10 or 100. So the intensity of a normal conversation is 100 times more intense than a whisper. Another example, if you wanted to look at the change in intensity in going from a whisper to a vacuum cleaner, the increase in intensity would be 10 times 10 times 10 times 10, or 10,000 times more intense. So the sound intensity of a vacuum cleaner is 10,000 times more intense than the intensity of a whisper. This last slide just shows some decibel levels of common sounds. Sounds that have a decibel level of 120 or greater cause pain and can damage your ears.